In this video, we're going to look at how to sketch the graph of a derivative from its original. There are a couple of features that we must consider when we're doing so. So let's just start by sketching a very simple graph. So let's say that we have a graph. Here's our y and x coordinates. And let's say that we just have a quick linear graph like this. Well, you know, we may call this linear graph y equals 2x plus 5. This might be what it looks like. And what we want to be able to do is to be able to ascertain what the derivative is going to be at any given point. So at any given point, what is the derivative means what's the slope of the tangent at these points. Now, because this is a straight line, we can ascertain that the gradient of the tangent is always going to be 2. This could be shown by deriving the function, and that gives us 2 like so. But when we come to sketching the derivative function, and we would label the y-axis not as dy dy, but dy dx and x, what we would have here is the derivative would be, or the function of the derivative would be dy dx equals 2, and that's a flat line going along in parallel to the x-axis. Okay. But what happens when we start dealing with a curve? So one tip that we would always say that you should look to do with sketching the derivative function based on the original graph is to try to line up the axes, or at least the x coordinates of the axes. So let's say that I had a function here that was, let's just say that it was a general parabolic curve. Okay, it looks like something there. Now there's some features of this curve that I want to highlight. One, in terms of the derivative, it's really important to find the turning point here, or the stationary point, because we know here that the gradient of the tangent is going to be 0. And what we can do is we can ascertain, so, you know, if we bring that line all the way down, and we could say that that point might be 2 or something like that. That would be x equals 2 in the dy dx axis. And then we can have a look at what happens in terms of our gradient either side of this value of y equals, oh sorry, not y, of x equals 2. So if I think about here, my gradients here are going to be positive. Okay, gradients of the tangent are always going to be positive, and they're going to be increasing. And here, the slope of my tangents are going to be negative. And it's really important that we identify which sections are positive and which sections are negative. So then when we come to sketch our graph, and it's also helpful to know what our graphs are doing, is we can say first and foremost that this turning point, in terms of the derivative, that's 0. And then we're going to have positive gradient, negative gradient, and here we have our derivative, or graph of our derivative. Now if we go a little step further, and let's say that we're dealing with a function, and let's make this a quartic. Okay, quartic looks like so. We're going to have y and x. We're going to try to line up our dy dx. And then we're going to highlight where our stationary points are. So I'd always highlight where our stationary points are going to be. So this stationary point, this has a stationary point, this has a stationary point, like so. And what this means is that our gradient at these stationary points are m equals 0, gradient of our tangents, of course. And what that translates to is with our graph of our dy dx function, they're going to be x-intercepts because they equal 0. Now we're also going to have a look at this graph and see what the slopes are here going to be. So here I've got a negative slope. Here I have a positive slope. Here I have negative. And here I have positive. So I'm going negative, positive, negative, positive. And I've got to be able to say that, okay, my graph is going to look something like that. Now, what we have in here is definite points of inflection. And the points of inflection is where the rate of change is sort of changing, or the double derivative, if you like. So this is, if you like, the steepest part of the graph that happens in this region. And this is expressed by a turning point with our derivative function. Now, what about when we talk about graphs that have points of inflection? So let's just use a simple graph here. Let's say a graph that looks like this. We'll have the coordinates 2 and 3. That's my y-axis, that's my x-axis. Bring this down to dy dx. X. This is obviously a point of inflection, so what it means is that the slope of the tangent is going to be 0, which means that my derivative is 0 at 2. Okay, we can show that by that kind of schematic. But here we have, if we consider both sides of x equals 2, here I have a positive gradient, and here I have a positive gradient. So how does that express itself when I sketch? Well, that's going to express itself like so. We can see here that, my dy dx is positive. It's getting, steeper as I go in towards x, or x approaches negative infinity. And as x approaches infinity, it gets steeper. And that's expressed within the function. Now, what about when we're talking about hybrid functions or piecewise functions? So I could have a piecewise function. Let's say that I have x equals 3, and let's say that I have a certain point going to this. That can be 5. And let's say that I have a negative parabola moving from that point backwards. Okay, so we can say here that we have a couple of things happening here. One, we can think that we have an m gradient of m equals 0, but this is questionable because that might be true for this section of the graph, or the parabolic side of the graph, but it's not true when I consider the linear side of the graph. So what I might have to do here is I do the same thing where I line my graphs up, dy dx. I'm going to put 3 in here because that's going to be an important component that we're going to look at. And I'm going to say here, well, m, we can just make an assumption, m equals 2. We know it's going to be positive. So I'm going to have 2 here, and I'm going to draw my gradient to 3. And this 3 is very important because we know that there's a change in the way of things work. And then this gradient here is always going to be negative. So even if that might be 0 at this point here, I know that it's going to be negative like that. Now, I just want to make sure that when I actually draw these, I'm going to put not included. And that's because there is no set gradient at this point. And that's something that you must consider.